Alright guys, this is the start of video number 2 where we are going to be dealing with free fall. I'm going to be working example problem number 7, which we worked part of in class but didn't finish, and then I'm going to be looking at chart number 9 and example problem number 10. So these are very similar to the ones we just did. You just have to remember things that are true for free fall. So here the problem says a rock dropped from a bridge high above the water hits the water after falling for 3 seconds. And then it asks us how high is the bridge above the water? What is the velocity of the stone when it strikes the water? With what speed would the stone have to be thrown to hit the water in just 2 seconds? And is the final velocity of the stone the same for this second case? So I don't know why I turned that. I tend to write with things sideways, so I'm actually having to try not to do that for y'all's sake. So, the first two steps, as always, it's actually more important now. We're going to set upwards as positive and downwards as negative, which actually means that our direction of motion is negative. The part of the problem we're working is while it's falling, it here being the rock. So let's set up our little chart. VF, VI, D, A, T. They give us exactly one number in this problem, 3 seconds. All right, well that is certainly not enough to solve a kinematic equation, but it's falling. That word, falling, should immediately clue you in, okay, this is a free fall problem. I should be doing something special. And the two things you should be doing special are that acceleration is actually g, and g is always pointed downward, and we set downward as negative. So ours is negative 10 meters per second squared. Notice that I didn't write that g was negative 10 because it doesn't necessarily have to be. It's just because we set downward as negative. I know that's a little weird and confusing, but we're going to survive together. So the other thing, we need one more number, right? The other thing is that things that are dropped start from rest. Don't get too complacent that all free fall problems start from rest. In baby physics, they do. For you guys, they don't have to. And we'll look at that. But here it does. It's dropped. It's starting from rest. So it's actually easier to answer part B first. But let's say that you were going into this problem and you committed a cardinal sin and did not read all of the parts before you started the problem, which you absolutely should do. But if you didn't, you wouldn't know that part B was easier, so you would be like, all right, let's just go, let's do part A. So part A asks how high, and we don't know final velocity. So which equation are we going to choose? We're going to choose this one. D equals VIT plus 1/2 AT squared. We don't have to do any algebraic rearranging because it's already solved for what we're looking for. So we get to write physics is done really early. And then we just have to plug in the numbers. We have 0 times 3. Please don't tell me that's 3, guys. I have very intelligent people do that far too often. Plus 1/2 of negative 10 times 3 squared. So negative 3 squared is 9. Negative 10 times 9 is negative 90. 1/2 of negative 90 gives me negative 45 meters. Now, this is the displacement of the rock. It has gone negative 45 meters. But someone brought up in class that that's not actually what Part A asks you. Part A asks you how high is the bridge. So the answer to that would be that the bridge is 45 meters tall. I don't know why I spaced that like entirely wrong. So because of the phrasing of part A, it's a positive answer, but the displacement here should be negative because it's falling downward. It's moving in the downward direction. So part B, what is the velocity of the stone when it strikes the water? There are two ways to think through this. One is to use the kinematic equation, which I'm going to do just to, show you. But you can also just think about what acceleration means. Acceleration is how much something is speeding up per second. Meters per second per second. And it's 10 meters per second per second. So at t equals 0, our velocity is 0. At t equals 1, we've sped up by 10, so our velocity would be 10. At t equals 2, it's sped up by another 10, so it would be 20. At t equals 3, another 10, so v equals 30. Let's prove that using our kinematic equations. So come back over here and look at our list. This time I'm going to say it's distance we don't know, it's final velocity we're looking for, which means we have to use our friendly first equation that we use the most often. And we say VF equals VI plus AT. It's already solved for what we want, so physics is done. Then we just say VF equals 0 plus negative 10 times 3. So final velocity is negative 30 meters per second. This should absolutely be a negative number. There's no weirdness like there was with part A where it's like how high versus displacement. It is negative no two ways about it because it is falling downwards. All right, so parts C and D are a little weirder. Part C asks, with what speed would the stone have to be thrown for it to hit the water in just 2 seconds? Now, I'm going to rewrite our whole chart. They want us to now do t equals 2 seconds. We still know, of course, that a is negative 10 meters per second squared. But now they're saying we don't know initial velocity. It wasn't just dropped, it was thrown downward with some initial velocity. We don't know anything about final velocity, that's part D. And so now we only have two numbers, but it's still being dropped from the same bridge, so we can use 45. Should we use positive or negative 45? What do you think? Yeah, we should use, that was like Dora the Explorer. Like, what do you think? You're right. God, I'm so sorry. Okay, You should use the negative version because that's the actual answer we got. That's displacement, which is what we're representing with the D here. We made it positive just because of the wording of the question, but we're going to include it as a negative number here. And if you do that wrong, I'm pretty sure this is one of the cases where you won't just get the right answer with the wrong sign. If you have that as a positive instead of a negative, you'll just get an answer that is completely wrong. So that needs to be negative here. So we're just going to solve the problem again. This time we're looking for VI, we don't know VF. We're going to use the same equation though. D equals VIT plus 1/2 AT squared. Oh man, I should rearrange it for VI. It's going to be gross looking again, but we can do it. D equals, no. D minus 1/2 AT squared equals VIT. You can't see what I'm writing. So D minus 1/2 AT squared equals VIT. We're going to divide both sides by T so that VI is by itself. And we get an equation that looks like this. VI equals D minus 1/2 AT squared over T. So negative 45 minus 1/2 times 10 times 2 squared all over 2. 2 squared is 4 times 10. Oh, negative 10 times negative 10. Okay, 4 times negative 10 is negative 40. Half of that is negative 20. So we have negative 45 minus a negative 20, which is actually 45 plus 20, which would give us negative 25. And then it's negative 25 divided by 2. I feel like my math there may have gotten kind of squirrely. Let me actually plug that into a calculator. This is why I don't do mental math, because I doubt myself. Oh, no, I did it right. Negative 25 divided by 2 is negative 12.5, and that's what you get when you plug it all in. So it had to have started with a velocity of negative 12.5 meters per second. Does it make sense for this number to be negative? What does it, well, let's start with what does it mean for it to be negative? It means that this velocity was downward, so the person threw it downward. Does that make sense? Yes, because it hit the water faster. If they had thrown it up, it would take longer to hit the water, so they need to have thrown it downward with a negative velocity for it to hit the water faster. So, part D. Part D says, is the final velocity of the stone the same for this second case? Now, because it doesn't actually ask you for the final velocity, you don't have to plug things in and find the final velocity. You absolutely can, and I probably will in just a second, just to kind of prove to you that what I'm doing is right. But you don't have to. This is again just a logic case, which is really what physics is all about. Let's think about it. This time it's only going to be accelerating for 2 seconds. So it's only going to speed up by 20 instead of speeding up by 30. But it's starting at 12.5. So is it going to be the same? No, because it's going to end up being somewhere around negative 32, 32.5 in this case. Yeah, and that should make sense that its final velocity would be faster if you throw it than if you just drop it. I'm actually not going to work that out. It's literally just using this equation again, except instead of 0 here, you have to put, let me see, you can't see what I'm pointing at, can you? Instead of the 0 here, you put 12.5, and then you put 2, and you plug it in, and you'll get 32.5. I believe in your ability to do that by yourself, but you don't actually have to, because the problem doesn't ask, what is the final velocity? It asks, is the final velocity the same? No. All right, so this next problem is finally the reason that we've been having to do that stuff where we're like, what part of the problem are we talking about? Blah, 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 blah. Because there are actually different parts to motion. Because what 9 and 10 are looking at, hopefully you did 8. 8 was a fill in the blank part that talked about this. And I'm going to post my key that has all the blanks filled in. So yeah, you can check your answers on that. But now we're talking about something that goes up and then back down. Like it's a thrown object. The only force acting on it is still gravity, so it's still considered free fall, but a portion of it is spent going upwards and then a portion of it is spent going downwards. So we need to talk about what that does. Sorry, adjusting. We need to talk about what that does for all of our variables. So this part's filled in for you. As it's going upward, upwards is set as positive and downwards is set as negative. Let me draw us a little picture here. So this is the first one. It's going upwards. It has a positive velocity that's decreasing in magnitude. Because think about it. It's going up, but it's being pulled on by gravity, so it's going to slow down. That's because gravity is always pulling downward. It's negative g. At the very top, its velocity, oh, you couldn't even see my beautiful picture. At the very top, its velocity is actually going to be 0. It comes to a stop. You don't have to worry about magnitude yet, because just at that one point, v is 0. But here's a very important point. The acceleration there is still negative g. That never changes. Even if the velocity is 0, the acceleration is not 0. Gravity doesn't just turn off for that split second. Then when it's going back down, over here, it's going to have a negative velocity. And what's its magnitude going to be doing? If we have a negative velocity and a negative acceleration from all of our talk on graphs, that's going to be increasing magnitude. It's speeding up, but it's speeding up in a downward direction. Now, there's something really nice about these problems, and that is that they're symmetrical. No matter how hard you initially throw something up, the time it spends going up is going to be equal to the time it spends coming down. Because how hard you throw it up is going to determine how far it goes up. And then that's going to determine how fast it's coming back down. And they actually all end up being the same. So let me kind of explain what I mean better looking at this problem. Number 10. An object is thrown straight up with an initial speed of 15 meters per second and caught at the same height sometime later. Find its maximum height, its total time in the air, and the acceleration at 2.3 seconds. So I'm going to draw another version of my picture. We have an object. This is t equals 0, our starting time. This is when it's caught again. We don't know when that happens. This is our height. We don't know what it is. What we do know is that vi over here is 15 meters per second. The really cool thing about free fall is that we can say confidently that that means the velocity over here is negative 15. That's just how gravity works. It's going to go up and come back down, and at that same point, so we're level. Oh, you can't see my pictures. I really need to pay better attention to what's actually happening. This is what I've been drawing all over. So sorry. 15 here, negative 15 here at the same level. If it kept falling, it would keep speeding up. But once it's at the level that it started at, it will be negative 15. Now, notice that I didn't actually label that as final velocity because we don't know that that's what we want to be our final velocity. We know the velocity one other place, which is right here at the top. Right here at the top, v equals 0 because it's going from a positive number to a negative number. It has to go through 0, and that happens at its maximum height. All right, so now we've already done one of the two things we're always supposed to do, which is establish which direction is positive and which is negative. Positive is up, negative is down. The second part is decide what part of the problem we're solving for. Suddenly that's important. The part of the problem we're going to solve for is the first half while it's going up. And what's it doing while it's going up? From our chart, we know that it's slowing down. So, we can now set up our chart. We do VI, VF, DAT, VI is positive 15, A is G, and in this case that's negative 10. Distance is what we're looking for, or displacement. And VF, because what we just said is that we're solving for the first half of the problem, VF is going to be 0. Now, you might ask, Ms. Schneider, why don't we just solve for the whole problem? Have VI be 15, VF be negative 15. The answer is because of what we're looking for. Remember that that D means displacement. What would its displacement be if we solved for the whole thing? It would be 0 because it looks like there's space here, but that's just because it makes it easier for me to draw. The person is throwing it straight up and catching it. So its displacement is 0, and we want to know its maximum height. That's the displacement when it's right here. So that's why we only want to solve for one half of the problem, because otherwise we'll get a displacement of 0, and that's boring and not what the problem is asking us. Okay, time is what we're not looking for. I don't know why I just got confused. So if we look up here for the one that doesn't have time, it's the one that has the squares. So we've got VF squared plus VI, no. VF squared equals VI squared plus 2AD. If we're going to solve that for D, I think we did this on one of the problems in the other set. We'll do it again anyway. It's going to be VF squared minus VI squared over 2A. If you don't believe me, go back. I did it slower the other time. But so physics is done. For the record, should we expect a positive or negative number here for distance, for displacement? Our displacement should be positive, right? Because it's going upwards and we set upwards as positive. So we should get a positive answer here. Let's see. We have 0 squared minus positive 15 squared over 2 times negative 10. So we are going to get a positive number because the negative and negatives are going to cancel. But I don't know what 15 squared is off the top of my head. 15 squared is 225 divided by 20. D equals 11.25 meters. That is the maximum height reached, and it is a positive number, so everything works out real nice. Now, there are 2 ways you could approach this second one, part B. One is that you could continue to do, and this is what I would tend to do. So let's just do it this way, and then I'll explain that we could have done it differently. Bloop, 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 bloop. Can you see what I'm doing? Sort of. All right, so I'm just going to do it like any of the others where now we're looking for time. I'm going to pretend we don't know distance. That means we're using VF equals VI plus AT. Solving that for time is VF minus VI over A. So 0 minus 15 over negative 10 equals T. T equals 1.5 seconds. You're going to be tempted to be like, draw a box around it, we're done, go home. Well, what did we just solve for? We solved for the first half of the problem. We found the time it would take to reach the top. Is that what it asked us for? No, it asked us for the total time, but it's symmetrical. So the total time would just be that T equals 3 seconds, 1.5 seconds to reach the top, 1.5 seconds to fall back down. Now, what I was saying that you could do this differently is that this time you could solve for the whole problem. You don't have the same problem you had with displacement where you're going to end up with 0. So what we could have done is with this same equation, we could have said, okay, VF is now negative 15. And we could have said, using that equation, negative 15 minus 15 divided by negative 10 equals T, and we would get T equals 3 seconds. Either way is fine. This just kind of proves, again, that it's symmetrical. It's always going to be true. Oh, and there is part C, but part C is just a trap. Part C asks you what is the acceleration at 2.3 seconds, and it makes it look like you're going to have to maybe do some math or something because it has that 2.3 there. What is the acceleration at any point in a free fall problem? Negative 10 meters per second squared. Meters per second per second. It doesn't change. It doesn't change ever. It doesn't matter at 2.3 seconds, at 1.8 seconds, at it doesn't matter. Gravity doesn't change. All right, I'm done talking to you guys. Have a nice rest of your break.